fairly obvious. Now, in general, is if you did G first, if you applied whatever this is, if you with the same, starting with the same set, the sets are the same, but if you put a G here and then an F here, so you reverse the order of your mappings, would you get the same thing? Like so if you did G first and then F, would the result be the same as doing F first and then G? So is that true in general or not? What's your intuition? What would you say? Well, let's now in general remember, if you want to refute something, if you suspect that this is probably not true, all you have to prove it false. Like if the mathematical hypothesis is this equals this for all cases, then you only have to find one counterexample to kill the idea. So let's pursue that route. Let's try to find a counterexample. Just a minute. Lost my felt tip top. Okay, now in this particular lecture, there are 7 theorems, and some of them quite detailed. A lot of details. So I'm using the text to prompt myself because too much for memory. Right. So now we're going to find a counterexample. So that f of x, this is straight out of the text. Okay. So f of x is 2x plus 1. Okay. And g of x is just 2x. Okay. So if our original x is just 1 and we're doing g first, so that'll be like fg, right? Fg of 1. Right? Remember the innermost one, it gets applied first. So the right hand one is applied first. So this g function, which is double the value, applies to 1. Well, that'll be f of. I hope you can see this. Oh, by the way, you'll probably those of you following this lecture by lecture, you'll probably be pleased to hear that I'm getting a new whiteboard in a matter of days. I think this is one. It's too small. So my writing should be bigger because I'm forced by YouTube upload slowness. I cannot use high definition. It takes too long. So I have to use standard definition. So that makes it harder for you to see small letters. So if I have the bigger board, I can write bigger letters. Also I have more space, so I can just write more. So it will be quite a bit bigger. So, hopefully in a few days. Right? And the quality is better. I mean, you see the white layer on the surface here is very thin, and underneath, stupidly, poor quality, is not white, it's silver. Really stupid. Okay, so g of 1 is what? Well, that's just 2. Okay. G of 1 here, so just 2. Now f of 2, can you see that's just 5? Yeah, f of 2 is 5. Okay, now the other way, now g of f of 1 will be, now what's f of 1? That's 3, okay? And g doubles it, so that's 6, okay? 5 and 6 are different, so therefore this is not equal, and therefore this is not equal in all cases because we have a counterexample. So that's wrong. Alright? Okay. Alright, so I guess you got the idea now of composite functions, functions that have parts like other functions. So we can start asking questions about about these composite functions, about H, this direct mapping that maps directly from big A to big C. Okay? So if you know something about the nature of the component functions, in other words f and g, if you know what type they are, for example, you know, if f is injective or surjective or bijective, and similar story for g, if it's injective, surjective, bijective, then what do you know about h? So what can you deduce about h if you know what types the functions f and g are? Right? You can start asking questions like that. Right? So here's an example. If f and g, well here, yeah, if f and g are both surjective, okay, I hope you've done your homework and you're quite familiar with what surjective means. Okay, so if these individually, if f and g individually, separately are surjective, what about the composite function gf? In other words, you apply f first, then g. Okay? Is it surjective? If both of these are surjective, is the composite function surjective? So there's a question. So this is an example. It's not a theorem. So, well, we could treat it as a theorem. So how would you go about doing that? All right. How would you do that? Now, so we're asking, in other words, we're asking is H surjective? Okay? We know these two functions are surjective, and we're asking now is H surjective? Now, how do you prove anything is surjective? Well, H will be surjective if for any element in C, in your codomain, you can find a corresponding element in your domain. Okay? That's the definition of surjective. Surjective means that every element in your set gets mapped to, right? There are no loners, no elements that are not mapped to. In a surjective function, every element here, every element in your codomain is mapped to. Okay, the whole set is covered in a sense. All right. Well, let's try to show that that is the case. Right. So we take a random element from big C. Let's call it little c. It's just a random element, and we're trying to show that it's covered by H. In other words, there will be some element in here in big set A that maps to this for all members of big C. Okay? So now C is just a random member, so it could be any one of them. So if we can find an element that maps uniquely to this little c from A, then we're okay, right? So let's try to do that. How to do that? Well, look, this little c gets mapped to uniquely, right, by G, because G is a proper function. It's a function. So that means there's some element in set big B, called little b, that maps to that. So this maps uniquely to that, all right? Because G is a function. All right, now we can apply the same kind of reasoning to B. So this, and you also know that F is a function. F and G are both functions, and they're both surjective functions. Okay, so that means that. Perhaps I should have emphasized it a bit more. Okay, so G is surjective, so every element is mapped. Okay? every element is mapped by G. So that means for this element C, there's a B in this set. All right? Now F is also surjective, so that means every element in this set is mapped to by one of these. And so let's say the one that does map to B is A, little a, that element there. Okay? So this one's mapping uniquely to that one, and little b is mapping uniquely to this one. Okay? So that means that C has A as its element that gets mapped to C, right, via H. And C is mapped to by B, and B is mapped to by A. So C has an A, for all C, that maps to it. Okay? So therefore this H here is surjective, because all elements here are mapped by elements in A. Therefore H is surjective. Okay? So you could have made it a theorem, but it's just an exercise. Alright, how about this? What if, now we just did the case when F is surjective and G is surjective, they both are. But what happens if, say, F is injective and G is surjective? Now remember, we're asking general questions like, what can you know about the nature, the type of function that H is, if you know what type of functions F and G are? Well, we just did one special case when both of them are surjective, then H is surjective. But what about this one? It's a bit different. Like F now is injective and G is surjective. So the composite function, GF, remember the right-hand side's the one that operates first. So GF, what will its type be? Will it be surjective? Will it be injective? Neither? What? In general, right? So let's again let's see if it's surjective. Now it gets a bit detailed, so I need to draw a diagram. So I'll draw three sets, right? Because we have two functions, so we need three sets. So